Hello everyone, welcome to Vyas Edification Kota. In this session, we are going to discuss class 12th chapter number 6 electromagnetic induction. Clear? In this session, you will find detailed video solution of each and every question of NCERT and exercise. Clear? As well as you will find some key concept behind that question also. Clear? So now we are going to discuss every question here. So concentrate on a screen. Now dear student, we are going to discuss question number 6.1, and in this question it is given to you, predict the direction of induced current in the situation described by following figure. Clear? So actually in this question from figure number A to figure number F, total these figures are given to you, and now we have to find what is exact direction of induced current in each and every case. Clear? So first of all, let us try to understand concept behind this question. Clear? Actually we know whenever there is some change in a magnetic flux is to be taking place, it means I can say whenever there is some change in magnetic field lines that will taking place, at the time we can see according to Faraday's law of electromagnetic induction, an induced EMF is generated. Clear? Whenever an induced EMF is generated, at the time I can say if a circuit is closed, an induced current will flow. Clear? So I think concept is very clear to you. So concept is very simple. Whenever there is some change in magnetic flux, induced EMF will be generated. If circuit is closed, induced current will be produced. Clear? If we talk about direction of that induced current is determined by Lenz's law. According to Lenz's law, the direction of induced current will be like this. It will try to decrease the effect. Clear? Or it will try to decrease that factor due to which that current is produced. Clear? It means I can say overall it will oppose the magnetic flux. Clear? So now we are going to discuss this case. So first concentrate here. For this is figure number A. In this question it is given to you, we have a bar magnet. Clear? And this bar magnet is coming to near to this coil, and this coil is at rest. Clear? Now we know whenever there is some relative motion between this coil and the bar magnet is to be taking place, definitely magnetic field lines that is associated with this coil, this changes. Clear? Now you can see if we talk about this case, this south pole, or we can say this bar magnet is coming near to this coil, at that time I can say the magnetic field lines that is going out from this particular area that increases. Clear? It means I can say here definitely an induced EMF will be generated because magnetic field lines is changing. It means I can say magnetic flux is changing. Magnetic flux is changing, it means definitely induced EMF will be generated. And because you can say here this circuit is given to you, this is closed, it means induced current will also be developed. But what will be direction of induced current? So I can say direction of induced current that is given by like this, that it will try to decrease these magnetic field lines or this magnetic flux. So now you can say, if you see it carefully, you can say if we let's suppose this induced current will flow in this direction. Clear? At that time you can say if you curl your finger like this. Clear? If you curl your finger like this, the direction of thumb, it will indicate direction of magnetic field. Clear? So at that time I can say due to this induced current, magnetic field in this direction increases. So definitely it is opposing this case. Yes or no? It means I can say if we talk about direction of induced current, so this current is actually flowing like this. It is going through this one, and again coming to this point. Clear? So what is direction of induced current? Directly I can say direction of induced current, this is given by from Q, R and P. Clear? So we have Q, R, P and again Q. Clear to you? Current is flowing in this direction. If you are looking from this side, from magnet side, you can see the direction of this current is clockwise direction. Clear? So now we can say Q, R, P, Q. This is direction of induced current. Clear? So this is all about part number A. Now we are going to discuss this figure number B or the part number B, and our objective here is to find what is direction of induced current. Clear? Now you can say again we have a bar magnet. Clear? And this bar magnet is approaching to this coil. So definitely I can say, because this is south pole, so magnetic field lines that is going through this section, that is increases. Yes or no? So at that time I can say induced current will be developed in this section or in this circuit. Like this, it will try to decrease this effect. Clear? So again I can say here, if I say this induced current will be like this. Yes or no? Clear? So now you can see, if you curl your finger like this, thumb will indicate in direction of magnetic field in this direction. Clear? But because south pole is coming near to it, definitely magnetic field lines is also increasing in this direction. Clear? So I can say this induced current will try to decrease the effect of that factor due to which it is we can say generating, or we can say it is producing. Clear? So directly you can see, if you see, this current is actually going like this, and it is going from P to R and then Q. Clear? So direction of induced current, I can say this is P R Q. P R Q, and again I can say that is P. Clear? So now if I say for this circuit, clear? Now you can say in this situation for this coil, you can see this bar magnet is actually going away from this coil. Clear? So when this is going away from this coil, definitely because this is a north pole, again I can say from north pole magnetic field lines always going outward direction. Clear? So as north pole is going away from this coil, definitely magnetic flux decreases. Magnetic flux decreases, it means I can say induced EMF will be generated, and induced current direction will be like this. It will try to increase this magnetic flux. Clear? So at that time again I can say here, direction will be generated, it will be like this. This is direction of induced current. Clear? Now you can see, if you see from this side, you can see that this induced current in anti-clockwise direction. Here this is in clockwise direction. In this case I can say this is anti-clockwise direction. So in anti-clockwise direction, if you curl your finger, definitely magnetic field lines, it will be a magnetic field direction is this one. Clear? So from here we can say actually this is going from Y, Z and X. Clear? Y, Z, X, and again you can say that is Y. Clear? So this is direction of induced current for figure number B. Clear to everyone? Yes. Now we are going to discuss case number C. In this case it is given to you tapping key just close. Initially we are assuming definitely here we have a coil. Clear? And we can say here we do not have any relative motion. Clear? But it is given here first this tapping key is open. Clear? It means I can say initially this is open circuit, but what will happening at the time this tapping key is just closed. Clear? When this tapping key is just closed, definitely I can say direction of current that is increased. I mean magnitude of this current that is increases. Clear? So now you can say if you are taking this as a front section. Clear? If I am taking this as a front section and this one is a we can say bottom one. Clear? Now if I am looking from this side, actually this you can assume, actually you can take this one as a behind one and this one is front one. Clear? So now you can say from this side, this is actually in clockwise direction. Clear? In clockwise direction, it means I can say if I curl my finger like this, listen carefully, if I curl my finger like this, at the time I can say magnetic field in this direction. Clear? Because current is increasing, so I can say magnetic field lines is increasing in this direction. Clear? So in this coil current will be generated like this, it will try to oppose these magnetic field lines. Clear? At that time I can say definitely this current will flow from this direction in anti-clockwise direction. Clear? So if you curl your finger like this, thumb indicate direction of magnetic field, and definitely direction of this magnetic field is in this direction, so it will try to oppose this effect. Clear? So now what is direction of induced current in this coil? So I can say here this is Z, X, Y, Z. Clear to everyone? So this is all about part number, or we can say part number C. Clear? Now we can say this is part number D, and in part number D it is given to you rheostat setting being changed. So let's suppose initially we have somewhat resistance. Let's suppose I am saying resistance value is decreasing, Let's suppose I am saying resistance value is decreasing. As resistance value decreases, at the time current that is flowing in this coil, that is decreases. Clear? I am assuming this side is the front side and we can say this is behind one. Clear? Now if I observe from this side, you can see here current is actually flowing in a anti-clockwise direction because you are decreasing resistance. Clear? So if you curl your finger like this, it indicates direction of magnetic field. Clear? So magnetic field direction we have in this direction. Clear? So definitely I can see the magnetic flux that is related to that coil, that is also changes. So whenever there is change in the magnetic flux is to be taking place, I can say induced EMF will be generated, and because this circuit is closed, so we can say here induced current will be developed. But this induced current will be developed like this, it will try to oppose this coach. Clear? So at that time I can say this current will be flow like this. Yes or no? Because if you see from this side, you can see this is in clockwise direction. Clear? So if you curl your finger like this in clockwise direction, thumb indicate direction of magnetic field, this one. Clear? So from here you can say clockwise means I can say clockwise. Yes. So current is actually flowing like the Z, Y, X and Z. Clear? Actually some student may say, sir, I am observing this is a backward one, this one is front one. So somewhat there may be confusion, but if you are taking one direction, let's suppose if you are taking this direction as anti-clockwise direction, if you are looking from this side, at that time you can say current that is produced in this coil in the clockwise direction. Clear? Because here we are actually decreasing resistance, that's why current is increasing, so it will try to oppose that current. Clear? So I can see here the direction will be Z, Y, X, Z. Clear? So this is all about part number D. Now if I talk about part number E, in part number E you can see tapping key just released. It means we can say initially, let's suppose this is a closed circuit and a particular amount of current that is already flowing in this circuit. Clear? But what will happen when we just release this tapping key? Just release means I can say value of current that is decreasing here. Yes or no? And you can say current is flowing in this direction like this. Current is flowing in this direction means if we observe from this side, if you observe from this side, you can see this is in the clockwise direction. Clear? So now if you curl your finger like this, magnetic field in this direction. Clear? It means I can say magnetic field lines that is associated with this coil, it will be like this. Clear? At the time, because value of current is decreasing, so I know if you are taking this as a solenoid, for solenoid I can say B, this is equal to mu naught Ni. So I can say when I is decreasing, clear, at that time magnetic field value is also decreasing. Clear? When magnetic field is decreasing, it means I can say value of B decreasing, it means magnetic flux decreases because flux is given by B dot A. When value of flux decreases, again I can say whenever there is some change in the magnetic flux is to be taking place, I can say induced EMF will be developed, and because circuit is closed, induced current will be flow. Clear? So at the time you can say current will be flow in this direction, it will try to increase magnetic field. So again you can say current will be flowing like this. Now you can say if you observe from this side, you can say current is flowing in anti-clockwise direction, also in the clockwise direction. Clear? If you are observing from this side, this current will flowing in a clockwise direction. You can say this is backward one, this is front one. Clear? So in clockwise direction, what is direction of magnetic field? In this direction. If you curl your finger like this, clear, like this, at the time we can say this is direction of magnetic field. So now you can say here we have direction of current X, R, Y and again X. Clear? So this is all about we can say yes. Clear? This is all about this part number E. Now here we have one more part. This is part number F. Clear? And in this question it is given to you. Here we have this. We can say this is a current carrying wire. Clear? And this current carrying wire, and we have this loop. Clear? Now you can say due to this straight current carrying wire, if you find direction of magnetic field, what is direction? Clear? Now you can say if I place my thumb in the direction of current, this curling finger represent direction of magnetic field. So now you can see here you will find magnetic field lines that is in the same plane of this coil. Yes or no? You will find magnetic field lines in the same plane. Clear? I can draw it like this. This one. Clear? Clear? You will find here direction of magnetic field like this. Clear? So now you can say these magnetic field lines are parallel to this coil. Clear? And I can say these magnetic field lines will not passes through the area of this coil. It means you can also say like this flux. Flux is given by that is B dot A. Clear? Or we can say this is equal to BA cos of theta. Clear? Now theta is what? Theta is an angle between B vector and A vector. Clear? So B vector you can say here we have tangential direction and A vector that is perpendicular one. So angle between magnetic field and area vector we have 90. So I can say this is given by BA cos 90. Clear? And you can say here this value 0. So magnetic flux that is associated with this coil is 0. So whenever there is no flux, I can say there is no induced EMF and no induced current is produced in a coil. Clear? So I can say what is answer of this question? No induced current. No induced current. Clear? So this is all about this question. Now student, we are going to discuss question number 6.2, and in this question it is given to you, use Lenz law to determine the direction of induced current in situation as shown in a figure. Clear? Now we can say in part number A it is given to you a wire of irregular shape. We have this irregular shape wire, it is turning into a circular shape. Now listen carefully. Now you can say actually we know basic concept is very clear in our mind. Whenever there is some change in a magnetic flux is to be taking place. Clear? At the time I can say induced EMF is developed due to Faraday's law of electromagnetic induction, and induced current is developed if circuit is closed. Clear? Now you can say if I am talking about flux, this is given by B dot A. Clear? And from here we can say this is equal to BA cos theta, where theta is angle between magnetic field and area vector. Clear? So my important conclusion is here, if we are talking about change in magnetic flux, it may take place due to these three things. Clear? Let's suppose we are taking here variable magnetic field. Clear? Let's suppose you can see in an part number A or in diagram number A, we can see magnetic field is perpendicular inward direction. So it is already given here in this question. If nothing is given, it means we are assuming this magnetic field is uniform magnetic field, but magnetic flux may change whenever there is a non-uniform magnetic field is there. Clear? So it may be possibility. We have another possibility when magnetic flux changes taking place, when we can say this area of this loop is changing. So you can say in this question area is changing. Clear? So whenever there is some change in area, we will find this phi changes. Or there is one more possibility, that orientation of this loop it may be changed. Let's suppose at this time we have a circular loop like this. Clear? And let's suppose we are rotating this circular loop about its vertical diameter. So let's suppose this one, and you are actually rotating it like this. So at that time I can say the magnetic flux that is linked with a particular area, that also changes. Clear? So it means I can say this magnetic flux may vary from three factors. Number one B, second one is A, and third one we can say angle between B and A. Clear? So in this question area vector is changing. Clear to you? Now listen carefully. In part number A it is given this irregular shape is changing into a circular loop. Clear? Circular loop means I can say this one. Clear? Now you can see if we are talking about area. Clear? If I am talking about area, for part number A this area increases. Clear? We are saying that we are not changing orientation, means I can say this area is perpendicular to magnetic field, and magnetic field we are also assuming uniform. It means I can say if area increases, I can say phi increases. Clear? Whenever phi increases, we can see induced EMF that is developed here, induced EMF that is also increases because phi is increasing. Clear? When induced EMF increases, I can say induced current that is produced like this. It will try to oppose it will try to oppose this coach. Clear? So now you can say, because area is increasing, flux is increasing, more magnetic field lines is going perpendicular inward direction, so current will be developed or induced current will be developed like this, it will oppose this coach. Clear? So we can say in this irregular shape, when it changes to this circular loop, I can say current will flow like this. Clear? Let's suppose I am taking here, this is A, this one is D, this one is C, and let's suppose this is B. So current is flowing like this. Clear? Why? Because if you curl your finger like this, here thumb will indicate direction of magnetic field. Clear? So direction of magnetic field due to this induced current in a perpendicular outward direction, but actually magnetic field is perpendicular inward direction. So this induced current is actually opposing this magnetic field lines. Clear? So I can say here definitely direction of current, this is equal to A, D, C and B. Clear? A, D, C and B. Clear? Now if we talk about part number B, in part number B it is given a circular loop being deformed into a narrow straight wire. Now you can say this is initial position, it is given to you. Clear? And after this initial position, I can say this is converting into a narrow wire. Narrow wire means I can say this one like this. This is narrow wire. Clear? Now you can say from here we can say this area is decreasing. Clear? Concept is very simple. Area is decreasing. So when area is decreasing, it means I can say flux decreasing. Area is decreasing, flux is decreasing. When flux is decreasing, it means I can say induced current will be developed like this, that it will try to increase magnetic flux. Clear? It means now you can say here magnetic field lines is perpendicular outward direction. These dots represent magnetic field perpendicular outward. Clear? And when we can say this magnetic flux is actually decreasing when area is decreasing, it means now current will be developed like this, it will try to increase this magnetic field. So now you can say when this magnetic field will be increased by this induced current, when I can if I curl my finger like this. Clear? If I curl my finger like this, thumb indicate direction of magnetic field. Clear? So you can say this is A dash, D dash, C dash, B dash. So definitely direction of induced current will be like this. Clear? So for part number B, I can say direction is given by A dash, D dash, C dash and B dash. Clear to everyone? So like this you can find here direction of induced current. Clear? Now student, we are going to discuss question number 6.3. In this question it is given to you a long solenoid with 15 turns per centimeter has a small loop of area 2 centimeter square placed inside the solenoid normal to its axis. Clear? So let's suppose I am taking here, this is a solenoid, let's suppose. Clear? Definitely this is solenoid, and let's suppose here we have a core that is inside this solenoid. Clear? It is given in a question. Yes, one more thing is given. Let's suppose current that is flowing here, this is I. Clear? A long solenoid are having number of turns per centimeter. So this is small n. I can say this is 15 turns per centimeter. 15 turns per centimeter. So can we convert it into turns per meter? Yes. So we can write like this. This is 15 into, we can say 100. This is now converted into turns per meter. Clear? So we can say number of turns per meter, this is given by 1500, this is 1500, this is turns per meter. Clear? Now it is given here a small loop of area 2 centimeter square. So let's suppose here we are placing a very small loop in this solenoid. Clear? And area of this solenoid, it is given to you 2 centimeter square, or we can say this is 2 into 10 to the power minus 4 meter square. Clear? Now, if the current carried by solenoid changes from 2 ampere to 4 ampere in 0.1 second, it means now we are changing current that is flowing in this solenoid. Clear? Now listen carefully. We know value of magnetic field. Value of magnetic field due to this solenoid at its axis, this is given by mu naught and I. Clear? When we can say when this value of I changes, again I can say this value of B changes. Clear? And when value of B changes, it means magnetic field, or we can say magnetic field lines that is associated this loop, this also changes. Clear? It means I can say when B changes, directly you can say phi changes. Clear? Whenever there is some change in a magnetic flux is to be taking place, I can say induced EMF will be developed. Clear? So I can say this is given by d phi by dt. E equal to d phi by dt. Clear? So this one clear? Now E equal to d phi by dt. It means induced EMF will be developed. Clear? So my objective is what? My objective here in this question is to find induced EMF. Clear? So directly you can say E, this is given by d by dt. I can say that is BA, phi equal to BA. Because area of this loop, this is small loop that is not changing. So we can say this is A, this is dB by dt. Clear? Now value of B for this solenoid, I can say this is mu naught Ni. Clear? So E value, this is given by A d by dt, and this is multiply mu naught Ni. Clear? Now we can say mu naught and N, this is constant, but current is changing with time. So directly you can say this is mu naught Na, and this is di by dt. Clear? Now we can place here value of all these parameters and we can get induced EMF. Clear? So concentrate here. Yes. So from here we can see value of induced EMF, this is given by mu naught. Mu naught value we have 4 pi into 10 to the power minus 7 multiply. I can say number of turns per meter. You know this is 1500 multiply. What about area? Area is given to you 2 into 10 to the power minus 4 multiply. This is delta, this is di by dt. So what is change in current? Change in current we can say this is 4 minus 2. Clear? And I can say this is dt. Dt means what is change total time taken 0.1 second. Clear? So now we can say induced EMF value, we can say this is 4 pi into 15 into 10 to the power minus 5 multiply 2 into 10 to the power minus 4 multiply 2 divided by 0.1. This is 20. Clear? So we can say this is 60 pi multiply, I can say 2 multiply 10 to the power minus 9 multiply 20. Clear? So we can say this is 12, I can say 12 pi into this 100, we can multiply it with this one. Clear? This is 2. Clear? Yes or no? 2 multiply 6, that is 12, 10 to the power minus 7 and 2. From here we can say this is 24 pi. Clear? And multiplied with 10 to the power minus 7 volt. Clear? So this is value of what? This is value of induced EMF. Clear? So concept is clear to you. Why? How can we say this induced EMF will be developed? Because B is changing. Why B is changing? Because I is changing. So I is changing means B changes. B changes means phi changes. Phi changes means induced EMF developed. Clear? So this is all about this question. Now we are going to discuss this question, question number 6.4, and in this question it is given to you a rectangular wire loop of side 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. Clear? So let us try to understand this situation. Let's suppose I am taking here, actually here we have two sides, so let's suppose I am drawing here. Clear? Let's suppose this is a rectangular wire, it is given to you, and here we have a small cut. Clear? Small cut means we can say here this loop is not a closed loop, this one is open. Clear? In this question it is given a rectangular loop having side 8 cm. I can say this one is 8 cm. Clear? And this is given to you, this is 2 cm. Clear? This one is 2 cm with a small cut is moving out of a region of uniform magnetic field. Clear? Uniform magnetic field of magnitude. So let's suppose I am assuming here magnetic field is in this direction. This is uniform magnetic field. Now listen carefully. So you can assume this black one is a uniform magnetic field that is perpendicular inward direction. Clear? I can say here if we talk about this question, what is EMF developed across the cut if the velocity of a loop is 1 meter per second in a direction normal to longer side. So first, if I am talking about part number A, let's suppose I am assuming this loop, or we can say this actually rectangular wire loop, it is moving in an upward direction, or we can say it is perpendicular to this longer side. Clear? Definitely, actually we have a one concept, when a current carrying wire is actually moving in a magnetic field, at the time an induced EMF will be developed. Induced EMF will be developed through this across this end. Clear? So what about the magnitude? Listen carefully. Velocity is given to you in this direction. Clear? I can say this longer side, it is given that is perpendicular to this velocity, and you can also observe here magnetic field, velocity vector and this length all are mutually perpendicular to Clear? So definitely you know here one formula, when B, I can say BVL all are perpendicular to each other, at the time you can write like this, induced EMF is given by BVL. Clear? So value of B we have that is 0.3. Clear? Velocity is given 1 centimeter per second, I can say this is 10 to the power minus 2 meter per second. What about length? Clear? Length is given to you 8 centimeter, so 8 into 10 to the power minus 2. Clear? So from here we can see this is given by 8 multiply 1, and this is 0.3, so 2.4 into 10 to the power minus 4 volt. Clear? So this is induced EMF when the longer side, when we can say this velocity is acting perpendicular to this longer side. Clear? So this is case number 1. Now let's suppose if I am talking about part number B. Clear? Or in part number B, actually this velocity vector or velocity is acting on a shorter side of a loop. So let's suppose in second case I am saying, let's suppose velocity is in this direction. Clear? Now again you can see here velocity, if I am talking about this distance, that is B, so V, B and capital B. Clear? Or you can say let's suppose this is V, capital B or this small b, all are perpendicular to each other. Again you can apply here we can say this formula E, it is given by B, V, L. Clear? L, instead of L I will write this is B. Clear? So value of B, this is given 0.3. What about velocity? Velocity is same, 1 centimeter per second, so 10 to the power minus 2. And what about this side? Side is given 2 centimeter, so 2 into 10 to the power minus 2. Clear? So from here we can say this is equal to 2 multiply this one, so 0.6 into 10 to the power minus 4 volt. Clear to everyone? So this is induced EMF that is developed across this end. Clear to everyone? Actually you can find also the direction of induced EMF. Clear? So now we can say actually here we have one more part, for how long does the induced voltage last in each case. So actually induced voltage will be developed across its end till we can say magnetic flux will change. Clear? Or there is a whenever this current carrying loop, or we can say this rectangular loop that remains in a magnetic field. Clear? So now we can say, can we find here total time taken in each case? Yes, I can say total time taken in first case. Clear? If I find here total time in first case T, this is given by, now I can say what is distance covered. So when this loop is going in this direction, distance covered in this magnetic field is only 2 centimeter. I can say that is distance covered about, and velocity. Velocity is given 1 centimeter per second. So I can say total time taken is 2 seconds. Clear? In case number 1. What about total time taken in case number B? Clear? I can say in case number B, total time is what? Total distance covered in the magnetic field, this is 8 centimeter. So 8 divide by, we can say what about velocity? This is 1, so this one. Clear? So from here you can say this is 8 seconds. Clear? So like this we can calculate here total time also. Clear? Okay. So this is all about discussion. Now dear student, we are going to discuss this question, and this is a question number 6.5. In this question it is given to you, a 1 meter long metallic rod is rotated with an angular frequency 400 radian per second about an axis normal to the rod passing through its one end. Okay. The other end of a rod is in contact with a circular metallic ring. Fine. A constant and uniform magnetic field, this is acting this is 0.5 Tesla. We have to calculate EMF developed between center and the ring. Clear? First of all, let us try to understand concept behind this question. Clear? So now concentrate here. Let's suppose I am taking this road. Clear? And let's suppose this road is actually hinged at this point, and this road can rotate about this hinge point. Clear? It is given here value of omega. We can say angular velocity, this is omega. Clear? Now let's suppose I am saying a uniform magnetic field is acting in perpendicular inward direction. Clear? A uniform magnetic field is acting in perpendicular inward direction. Clear? Now let's suppose I am taking here a very small element. Clear? And let's suppose this distance of, or we can say total length of this element is dx. Let's suppose I am saying this is going with the velocity v. From here this distance is x. Clear? Now actually we can say, because this is a road and for each and every point distance from this end is different, so definitely we can say area that is covered in a particular area covered in a one revolution that is different for different particles. Yes or no? That's why I am taking here a small element. Clear? Now listen carefully. This magnetic field V, this velocity v, and this length dx, we can say all are perpendicular to each other. Yes. So from here we can say dE value we can write like this. This is bv dx. Clear? bv dx. So if we find here net induced EMF, this is given by bv dx. Clear? Now v we can say this v equal to r omega. So here we can write like this dE. It may be right like this. B velocity, we can say this is x omega. Clear? And it is multiplied with dx. Clear? Now we can place here value from 0 to L, and I can say, let's suppose this is 0 to E. Clear? So induced EMF, I can say E, this is given by, you can represent by E. Clear? So E, this is given by B omega integration x dx from 0 to L. Clear? So from here I can say value of E, this is given by B omega. Clear? I can say this is x square by 2 from 0 to L. Clear? So induced EMF, this is given by B omega by 2, and this is L square minus 0. Clear? So from here we can write like this E, this is given by 1 by 2 B omega L square. Clear? So this is what? This is induced EMF that is developed between center of this ring. Clear? And we can say this is, let's suppose here we have a ring, so center of the ring and this end. Clear? So in this question you have to utilize directly this formula. Clear? Induced EMF developed, this is given by half of B omega L square. Clear? So now we are going to solve. Clear? Now from here we can say, let's suppose I am saying now induced EMF is like this, 1 by 2 B omega L square. Clear? Now 1 by 2 value of B is uniform 0.5 Tesla. So 0.5 multiply omega is also given to you. Yes, 400 radian per second multiplied with L. L is given. Yes, that is 1. So this is 1 square. Clear? So from here we can write like this. This is 1 by 2 multiply 0.5 into 400. Clear? 0.5, this is equal to what? 1 by 2. So I can say this is 1 by 4 multiply 400, and this is equal to what? 100 volt. So now dear student, we are going to discuss question number 6.6. Clear? And in this question it is given to you a circular coil of radius 8 cm and number of turns, that is 20, is rotated about its vertical diameter with an angular speed of 50 radian per second in a uniform horizontal magnetic field of magnitude 3 into 10 to the power minus 2 Tesla. So let us try to understand given situation. Now it is given here we have a circular coil. So let's suppose this is circular coil. Clear? This is given to you circular coil. It is having radius 8 cm. So I can say value of R we have, this is 8 cm. Clear? And number of turns, this is given to you, this is 20. Clear? So radius is given, number of turns is given. It is rotated about its vertical diameter. Vertical diameter means we can say this is the diameter. So this is diameter and this is axis along diameter, clear, and it is rotated about this diameter, and angular velocity, this is also given to you, angular speed omega with 50 radian per second, fine. And in a uniform magnetic field, so let's suppose I am assuming here uniform magnetic field, this is exerted in perpendicular inward direction, clear. So this is uniform magnetic field, and value of B, this is given to you 3 into 10 to the power minus 2 Tesla, clear. And now we have to find here, obtain the maximum and average EMF induced in the coil. Now you know very well, if we are talking about induced EMF, clear. So induced EMF will be generated whenever there is some change in a magnetic flux is to be taking place, clear. But now we also know how can magnetic flux changes. Magnetic flux, it may change due to change in due to change in magnetic field, due to change in area, and due to change in orientation. So in this case you can see magnetic field is a constant, radius is also constant. It means the orientation of, or we can say angle between area vector and magnetic field is changing, clear. So we can say here we are having some change in a magnetic flux. So whenever we have a change in magnetic flux, we can say there is an induced EMF, clear. So we can write like this, E, this is given by E naught, I can say this is sine of omega t, clear. E equal to E naught sine of omega t, clear. Now we can say value of our objective is what? Our objective here is to obtain maximum and average value of EMF, clear. So I can say this value E naught. E naught means we can say this is maximum value of induced EMF, and this is given by band omega, clear. So when you derive this expression, you will find E equal to E naught. E naught, in the place of E naught you can say this is band omega, I can say this is sine of omega t, clear. Now we can place here all the values. So value of B is given 3 into 10 to the power minus 2, clear. What about area? Area is given, it means radius given. So I can say this is pi r square, pi 8 into 10 to the power minus 2 whole square, multiply. What about number of turns? Number of turns is given, this is 20, and multiplied with omega. Omega is given, yes, this is 50 radian per second, clear, 50 radian per second. So from here we can say 50 multiplied 20, this is 1000, 10 to the power 3. So 3 into, I can say 10, only 10, because 10 to the power 3 minus 2 becomes only 10, clear. Multiply pi into, I can say this is 8 multiply 8 multiply 10 to the power minus 4, clear, 10 to the power minus 4, clear to everyone. Here we have 1000 multiply this one 10 to the power minus 1, clear, yes or no? This is 1000 multiply this one 10, it means only 10, clear. This is 3, this one is pi, 8 multiply 8 10 to the power minus 4, clear. So from here you can say this is 30, pi multiply 64 multiply 10 to the power minus 4, clear. So you can multiply here 30 with 64. So we are getting here, this is we can say 12, we have 192 pi multiply 10 to the power minus 3 volt, clear. Now you can multiply 192 with 3.14, clear. So directly you can say 192 3.14, clear. So can you multiply it? Yes. So approximately, let's suppose we are multiplying with 3, clear. So I can say here exactly value you will also calculate, this is 8, we have 36, we have 3, so 7, 2, 9, 1 multiply, I can say this is 6, clear, 9, 3, 27, so this is 7, we have 2, this one, clear. So if you add it, you will find this value, clear. So from here you are calculating value of E naught, means maximum value of induced EMF, this is given by, I can say 8, we can say this one is 8, clear, 9 or 7, 16 or 6, 22, clear. We can say this is 2, so 2 or 1, I can say that is 3, 3 or 7, that is 10, and this one, clear. From here you can say you are getting here decimal after 1, 4, so this one, clear, and here we are having 10 to the power minus 3, clear. So from here we can write like this, this is given by 0.602 volt, clear. So this is maximum value of induced EMF, clear. So one objective is clear to everyone? Yes. Now our second objective in this question, here is to find average EMF. Clear? Now you can say actually this EMF is varying according to E equal to E naught sin of omega t. Clear? So we can say this EMF is varying sinusoidally. Clear? And average value of sine in a complete cycle is 0. So I can say average value that we will find here in terms of induced EMF, that is 0. Clear? So peak value is given by 0.602 volt and average value this is equal to 0. Clear to everyone? So, yes. Now yes, now we are going to discuss the rest of part of this question. Clear? Concentrate here. This value will be useful for us, that is 0.602 volt. Clear? Yes. I think you are getting my all points. Clear? I am trying to clarify your I am trying to give you all the concept that is related to this question. Clear? Now listen carefully. So from here you can see, if I talk about next part, if the coil forms a closed loop, okay, and resistance is given to you 10 ohm, so value of R that is equal to 10 ohm, it is given. Now we have to calculate the maximum value of current in a coil. Clear? So maximum value of current, I can say this is given by E naught by R. Clear? Value of E naught we know, this is 0.602 divided by, I can say that is 10. Clear? So from here we can write like this, 0.0602 and this is ampere. Clear? So this is maximum value of current. Clear? Now we have to calculate here average power loss due to joule heating. Clear? So I can say average power heating. Clear? Average power heating equal to what? I can say this is given by I RMS square multiplied with R. Clear? Or if it is given here average power loss we have to find. Clear? So for that I will write here this is I RMS. Clear? I RMS we can say this is equal to what? I naught by root 2. I naught, so we can write like this, I naught square divided by 2 multiplied with R. Clear? 1 by 2. Clear? I naught square. So we can say this is 0.06 multiply 0.06 multiply. Clear? And value of R that is equal to 10. Clear? So now you can say here we can say this is 0.03. Clear? Multiply this is 0.6. Clear? So from here we can write like this, value of average power. Value of average power, this is given by we can say 18 divided by, clear, 18 divided by we can say 1000. Clear? So we can say this is equal to 18, directly you can say 18, this is 1 and 18 divided by 1000 watt. Clear? So this is average power, and now you can say from where this power actually you are getting. Actually this coil is rotated by some mechanical means. Clear? Mechanical means we can say here we are, let's suppose here we have a motor. Clear? And this motor is actually rotating this coil. Clear? So we can say from external source we are getting that energy. Clear? And that energy is actually dissipated in the form of heat. Clear to everyone? So our objective is what? To calculate power loss due to joule heating. So power loss means our objective here is to calculate, this is power. Clear? But can we find here that is power loss? Yes, that is I square R. Clear? So this is all about this question. Clear? Now we are going to discuss question number 6.7, and in this question it is given to you a horizontal straight wire 10 meter long extending from east to west is falling with the speed of 5 meter per second. Clear? So let's suppose I am saying let's suppose this is a horizontal straight wire. Clear? And let's suppose this direction is east direction and this one is west direction. Clear? Length of this wire is given to you L, that is equal to 10 meter. Clear? Okay. It is extending from east to west direction. Fine. Falling with a speed of 5 meter per second. So definitely when it will fall in downward direction, not in a vertical direction. Clear? So I can say here value of V, this is given 5 meter per second. Okay. At right angle to horizontal component of earth magnetic field. Clear? So definitely we can say in this direction we have east, this is west, I can say this one is north and this one is south. Clear? So if I am talking about horizontal component. Clear? So horizontal component I will find in what direction? From north to south. Clear? So magnetic field lines always move from north to south. So from here we can see I am indicating this one like this. Clear? So in this direction we have horizontal magnetic field. Clear? Now what is our objective? What is instantaneous value of induced EMF? Clear? So instantaneous value of induced EMF, this is given by, listen carefully. Now we know this is given by E equal to E naught sin of omega t, number one. Or actually you can say whenever we have a wire, clear, and it is placed in a magnetic field and it is having certain velocity, definitely induced EMF will be generated. Clear? And most important part is here, this horizontal component of magnetic field, velocity and length of this wire all are mutually perpendicular. Clear? So now we can say, we can write like this, this is given by B. B means horizontal component of R, V means velocity and L is a length, BVL. Clear? So from here we can say BH is given by, I can say 0.30 into 10 to the power minus 4 multiply. Clear? 10 to the power minus 4 multiply. What about velocity? I can say 5 meter per second. And what about length? Length is given to you, this is 10. Clear? So we can say 0.30 into 50 into 10 to the power minus 4. Clear? So I can say this is divided by 100. Clear? So from here this one cancelled out, and directly we can see here this one cancelled. So 15 into 10 to the power minus 4 volt. Clear? So this is instantaneous induced EMF. Clear? Why I am saying this is instantaneous? Because at this time all are mutually perpendicular. Clear? Now this is all about part number A. But if I am talking about part number B is what is direction of this EMF. Clear? Now you can say, let's suppose my fingers are representing direction of magnetic field in this direction. Clear? Now we can say thumb indicates direction of velocity. At the time this palm is representing direction of higher potential. Clear? So I can say at this time I can say this west end is at higher potential and this one is at lower potential. Clear? So what is direction of EMF? Direction of EMF directly we can see from west to east. From west to east. Clear to everyone? West to east. Clear? Okay. Now if I talk about part number C, in part number C it is given which end of the wire is at higher electric potential. Definitely you can say west end is at higher potential. West end at higher potential. Higher potential. Clear to everyone? So this is all about this question. Now we are going to discuss question number 6.8, and this question is looking very short, and definitely this question is very easy. It is actually formula based question. Clear? Now let us try to understand. Current in a circuit falls from 5 ampere to 0 ampere in 0.1 second. It means I can say value of I1 we have 5 ampere, and I can say value of I2, this is given to you 0 ampere. Clear? And it is also given here time difference, this is 0.1 second. Clear? Now it is given if an average EMF of 200 volt is induced. So I can say average EMF, it is given 200 volt. Give an estimate of self-inductance of a circuit. Clear? So whenever I am talking about self-inductance, do you know what is relation between this induced EMF and self-inductance? Yes, a very popular relation we have, E. This is given by minus L di by dt. Clear? You can also write like this. If I am talking about average, this is equal to minus L change in current over change in time. Clear? Now E average, this value is given to you because it is already given average, so this is 200 minus L, and delta I equal to what? We can say this is I2 minus I1 divided by delta T. Clear? From here we can say this is 200 minus L I2. Value of I2 we have, this is 0. So 0 minus 5 divided by delta T, this is 0.1. Clear? So from here we can see 200, this is equal to minus L, and I can say minus 5 divided by 0.1. Clear? We can say this minus and minus becomes plus, and this decimal I can say that is equal to 10. So 200, this is given by L, and I can say this is 50. Clear? So from here we can say value of L, we can see 200 divided by 50, and this is given by 4 Henry. Clear? This is given by 4 Henry. Clear? So correct answer 4 Henry. Clear? Now we are going to discuss this question number 6.9, and in this question it is given to you a pair of adjacent coil has a mutual inductance value 1.5 Henry. Clear? So value of capital M, this is given to you 1.5 Henry. Fine. If the current in one coil changes from 0 to 20 ampere, means we can say change in current we are having, this is 20 minus 0, and this is equal to 20 ampere. Fine. And change in time, it means total time taken, it is given to you 0.5 second. Fine. What is the change of flux linkage with the other coil? Clear? It means our objective here is to find change in flux. Clear? Now dear student, do you know what is concept we will utilize in this question? Clear? Actually, concept is very simple. What is that concept? E. This is given by minus d phi by dt, and because we are talking about mutual inductance. Clear? So for mutual inductance I can say this is M di by dt. Clear? This is what? This is the change in the flux, or we can say in mutual inductance we always find there is some change in the current that is to be taking place in a primary coil, and due to that change in current there are some change in the flux is to be taking in secondary coil, and vice versa is also possible. Clear? So I can say here we can write like this, minus time d phi. Clear? If we compare both this one, minus d phi, this is equal to M times of di. Clear? So from here we can also write like this, change in flux. Clear? So change in flux, this is given by M times of change in current. Clear? So change in flux we have? No, this is our objective. What about mutual inductance? This value is given 1.5 Henry, and change in current, that is 20. Clear? So from here you can say this one and this one cancelled out, and this is 30 Weber. Clear? Yes or no? So this is all about this question. Clear? Now student, we are going to discuss question number 6.10, and in this question it is given to you a jet plane is travelling towards west at a speed of 1800 km per hour. Clear? So first let's draw here a jet plane so that we get clarity more of the concept. Clear? So now concentrate. Let's suppose this is one neck, we can say this is another one. Let's suppose this is like this one. Clear? Now this is one, and I can say it is just like this. Clear? Here we have this one. Clear? And this one. Clear? From here we can say this is the wings of this, we can say that is plane. Here we are having, just a minute. Yes. So this one. Clear? And we can say it is just like this. Clear? And here we have another span, so this one and this one, and I can say something like this. Clear? So let's suppose this is a plane. Clear? Let's suppose this is plane. Definitely this side again we have this one. Clear? So now let's suppose this is plane. In this question it is given this jet plane is travelling towards west. So definitely we know in this direction we have east, this is west. So it is actually going in this direction. Clear? Velocity is given to you 1800 km per hour. So we can convert into meter per second, and we can say this is 500 meter per second. Clear? 500 meter per second. Okay, fine. Now a jet plane is travelling towards west at a speed of 500 meter per second. What is voltage difference between ends of our wings having a span of 25 meter? So from here you can see, if I draw here total span, it means length of these wings, this is given to 25 meter. Clear? Now you can see here velocity is perpendicular to this length. Clear to you? Now one more thing is given here, the earth magnetic field at a location has a magnitude of 5 into 10 to the power minus 4 Tesla. Clear? So let's suppose if I draw here magnetic field. So let's suppose earth magnetic field is like this. Clear? Because deep angle is also given to you. So definitely we have north in this direction, this one is south. So definitely net magnetic field we can say horizontal component we will find in this direction, and we will find a vertical component in this direction. Clear? So this is component of horizontal, this is vertical component. Clear? And we can say this is angle of dip. Clear? Now you can say this horizontal component is parallel to this length. It means this will not responsible for induced EMF. Now but you can say this vertical component of earth magnetic field in the downward direction. Here we have this is L and this one is V. So I can say vertical component of magnetic field, length and velocity all are perpendicular to each other. Clear? So from here we can see value of E. Clear? Value of E, this is given by BV, and I can say this is V and multiplied with L. Clear? So from here we can say E, value of BV. BV means we can say vertical component. Vertical component we can say this is B sine of del. Yes or no? Clear? And what about V? V is given to you 500 and multiplied with length, that is 25. Clear? So value of B. Value of B, it is given in a question, 5 into 10 to the power minus 4 multiply, I can say sine, and what about del? Angle of dip 30 degree. Clear? 30 multiply 500 multiply 25. Clear? So from here we can write like this. This is equal to 5 into 10 to the power minus 4 into 1 by 2 into 25 into 500. Clear? So from here we can see this is 125 into we can see 5 into 10 to the power minus 2 divided by 2. Clear? Yes or no? We can say 5 multiply 10 to the power minus 2, 25 and multiply 5, 125 divided by 2. So from here we can say this is 625 divided by 2 into 10 to the power minus 2. Clear? So from here can we find value of E? Yes. Now you can divide here 312.5 into 10 to the power minus 2, or you can say this is equal to 3.125 volt. Clear? So I can say this is induced EMF that is developed in the wings of this aeroplane. Clear to you? So this is all about this question. Now student, we are going to discuss this question number 6.11, and in this question it is given to you, suppose the loop in exercise 6.4 is stationary. Clear? So in exercise 6.4 it is given to you, let's suppose I am assuming this is magnetic field perpendicular inward direction. Clear? Magnetic field, this is perpendicular inward direction. Clear? Let's suppose I am taking here a loop. Let's suppose this is loop. Clear? And actually it is given here this loop is in cut. Clear? But it is also given here in exercise number 6.4 that this value of this length. Clear? This length is given to you 8 centimeter. Clear? And this value is also given to you, this one is 2 centimeter. Clear? Now let us try to understand this question. Now it is given that this loop is stationary. Clear? The loop is given, this is stationary. Okay, I can say this is stationary. But the current feeding the electromagnet that produces magnetic field gradually reduced. It means what I am saying to you. Actually, definitely we place here this loop, and definitely here we have a magnetic field. But that magnetic field comes from where? Actually that is magnetic field is produced by a electromagnet, and in electromagnet we produce magnetic field due to current. But in this question it is given to you the current feeding electromagnet is now reducing, and so that we can say the value of this B is decreasing from initial value. Initial value is given Bi, this is 0.3 Tesla. This is initial value at the rate of 0.02 Tesla per second. It means I can say value of dB by dt we have 0.02. This is Tesla per second. Clear? Now it is given if the cut is joined and the loop has a resistance of 1.6 ohm. 1.6 ohm. Now our objective here is to find power dissipated by loop. Clear? So very simple question we have. Clear? Now what we can do here? First of all, we can write like this: induced EMF in magnitude, this is given by d phi by dt. Clear? Phi we can say that is equal to what? Ba. Clear? And from here you can also write like this is A dB by dt. Clear? So from here we can say this is average induced EMF. This is given by area. Area we have 8 into 2 into 10 to the power minus 4 multiply dB by dt. Clear? dB by dt is given, this is 2 by 100. Clear? So from here we can write like this, 2 multiplied to 4 and 4 we can say 32 into 10 to the power minus 6 volt. Clear? So 8 multiply 4, 32 multiply 10 to the power minus 6 volt. Clear to everyone? Now my here next objective, because this is loop, I can say induced current. Induced current is given by E by R. Clear? Value of R is given to you, this is 1.6 ohm. So I can say 32 divided by 1.6 into 10 to the power minus 6 ampere. Clear? From here we can say if we remove this decimal, clear, here we become 10 to the power minus 5 and directly you can say 2 into 10 to the power minus 5 ampere current we are getting. Clear? 2 into 10 to the power minus 5 ampere. Clear? Yes. But what is our objective? Our objective here is to calculate power, how much power is dissipated. Clear? So power dissipated, how can we find power dissipation? Power dissipated. Clear? So we can find power, this is given by I square R. Clear? Value of I we have 2 into 10 to the power minus 5 multiply 2 into 10 to the power minus 5 multiply value of R, this is 16. Clear? I mean 1.6. Clear? So from here you can say this is 4 into 10 to the power minus 10 multiply 16 divided by 10. Clear? So I can say this is 64 into 10 to the power minus 11 and I can say this is watt. Clear? So I can say this much amount of power is dissipated. Now you can say, so, from where we are getting this power, or from where we are getting this power is dissipated. So actually now you can say in this question actually we are reducing current. It means whenever we are reducing current, it means we are reducing from some external source. So we are getting that energy from an external source. Clear? So this is all about this question. So dear student, we are going to discuss question number 6.12. Clear? In this question it is given to you a square loop of side 12 cm with its side parallel to x and y axis is moved with the velocity 8 cm per second in a positive x direction. Clear? So first of all, let's suppose if I am drawing here, let's suppose I am saying this is z axis, I am taking this direction as z axis. Clear? This one is what? This is y axis and this one is x axis. Let's suppose. Clear? Now here it is also given to you actually sides of this square lies parallel to x and y axis. It means I can say this square loop is lie in xy plane. Clear to you? So let's suppose this one. Clear? It is also given this loop is moving with a velocity of 8 cm per second in positive x direction. So I can say velocity is in this direction and value of velocity is given 8 cm per second. So I can convert it into meter per second. So this one is meter per second. Clear? Yes. Now we can say side of this square loop is given. It means we can also find here area. Clear? What about area? Area is given by 12 into 12 into I can say 10 to the power minus 4 meter square. Clear? Okay. Actually it is moving in a positive x direction in an environment containing a magnetic field in positive z direction. Clear? So I can say magnetic field is acting in this direction. So magnetic field in this direction, that is B. Clear? Yes, magnetic field is acting in this direction along positive z direction. Fine. And it is also given the field is neither uniform in space or nor constant in time. It means I can say value of magnetic field, this is changing with respect to x as well as with respect to time. Clear? It means I can say value of magnetic field is changing with respect to x as well as with respect to t. Clear to everyone? So it is given in a question. It means I can say this magnetic field is a non-uniform magnetic field. Clear? Now it is given, it has a gradient of 10 to the power minus 3 Tesla per centimeter along negative x direction. It means I can say dB by dx, this is given to you 10 to the power minus 3 Tesla per second. So 10 to the power minus 3 Tesla per centimeter. Centimeter means you can convert into meter, 10 to the power minus 2 meter. Clear? So from here we can say this is equal to 10 to the power minus 1 Tesla per meter. Clear? Okay. Now we can say it is also given to you here. It has a gradient of this one along negative direction, and it also decreases with time with 10 to the power minus 3 Tesla per second. Clear? So we can write like this, dB by dt. Clear? dB by dt, this is equal to 10 to the power minus 3 Tesla per second. Clear? Now we have to determine direction and magnitude of induced current in the loop. Clear? If resistance is 4.50 milliohm. Clear? It means this is equal to 4.5 into 10 to the power minus 3 ohm. Clear? Now you can say, sir, why this induced EMF will be produced? Induced EMF will be produced because value of magnetic field is changing with space and time. Clear? Now we are going to discuss first value of that induced EMF. Clear? So listen carefully. Now we can say induced EMF. First of all, we are finding this induced EMF due to changing of magnetic field in space. Clear? So I can say E1, this is given by, we can say that is d phi by dt. Yes or no? D phi by dt. We are just finding here magnitude. Clear? So d phi by dt means we can say this is d by dt and multiplied with dm. Clear? Now you know cross section area. Area is same. So I can say this is equal to A dB by dt. Clear? Actually here we are finding induced EMF with respect to space. Clear? So with respect to space means we can also write it like this. This is dB by dx dot dx by dt. Clear? Now we know dx by dt. Dx by dt equal to what? This is velocity. Clear? So A V, I can say this is dB by dx. Clear? A V, this is dB by dx. Clear? This is value of E1. Clear? So from here, if we put here value of A, V and dB by dx, A is given to you. Yes. Value of A we have, that is 12 into 12. Clear? 12 into 12 into 10 to the power minus 4 multiplied. What about velocity? Clear? Velocity. What about velocity? Velocity is given to you. This is 8 into 10 to the power minus 2. Clear? So 8 into 10 to the power minus 2. And what about dB by dx? dB by dx, you know, this is 10 to the power minus 1. So 10 to the power minus 1. Clear? So from here we can write like this. This is equal to 144 into 8 into 10 to the power minus 4, and here we have minus 3. So 10 to the power minus 7. Clear? So we can also write like this. This is 1.44 into 8 into 10 to the power minus 5. Clear? So if we multiply it with 8, we can say this is, we have 32. So we have 3, we can say this is 35 and this one. So 11.52 into 10 to the power minus 5. Clear? So we can say this is in volt. Clear? So I can say this is induced EMF due to change in magnetic field with space. Clear? Now we can also write like this, induced EMF, we can say induced EMF due to change in magnetic field with time. Clear? So we can also write like this. This is equal to dB by dt. Clear? Area is given to you, 12 into 12 into 10 to the power minus 4 multiply. What about dB by dt? Clear? So dB by dt, this is given to you 10 to the power minus 3 Tesla per second. Clear to everyone? So 10 to the power minus 3. So we can say 144 into 10 to the power minus 7. Clear? So if you convert in this form, I can say we can write like this, 1.44. Clear? 1.44 into 10 to the power minus 5 volt. Clear? So this is value of induced EMF. Clear? So from here we can say value of E, this is given by E1 plus E2. Now why I am adding here both induced EMF? Because you can see here, if we are talking about this magnetic field is decreasing with respect to position, and this is also decreasing with respect to time. Clear? In both cases we can say magnetic field is decreasing. Clear? So it means induced EMF will be produced like this. It will try to increase magnetic flux. Clear? So finally I can say I can write like this, E equal to E1 plus E2. Clear? And if I put here value of E1 plus E2, this is equal to 11.52 plus 1.44 and multiplied with 10 to the power minus 5. Clear? So now if you add it, you can say this is 6, this one is 9, and this is 12.96 into 10 to the power minus 5 volt. Clear? Now Our objective in this question is to find induced current. Clear? So induced current we can write like this. This is E by R. E is given 12.96 into 10 to the power minus 5 divided by, what about resistance? Clear? Value of resistance is given 4.5 into 10 to the power minus 3. So 4.5 into 10 to the power minus 3. Now let's suppose if we find here approximate result, I can say this is 13. So 13 into 10 to the power minus 2 divided by, I can say this is 9 by 2. Clear? So this is 9 by 2. Clear? So from here we can say 26 by 9 into 10 to the power minus 2 ampere. Clear? So now you can say this is near about 3, because 9 multiply 3, 27. So we can see we are getting answer near about 3. Clear? This that is 3 into 10 to the power minus 2 ampere. Clear? So this is value of induced current. Clear? So this is all about this question. Clear? We are going to discuss question number 6.13, and in this question it is given to you, it is desired to measure the magnitude of field between the poles of a powerful loudspeaker magnet. Okay, a small flat search coil of area 2 cm square with 25 closely wound turns is positioned normal to the field direction. Clear? So let us try to understand this given situation. You can see initially it is given that B and A. Clear? Initially you can say what is given here. Listen carefully. A small flat search coil of area is positioned normal to field. Clear? So it means I can say this situation is like this. Let's suppose this is a coil. I am saying we can say this is direction of area. Clear? Actually we can say this plane of a coil is perpendicular to magnetic field. Clear? What I am saying to you, the plane of this coil is perpendicular to magnetic field. Clear? Perpendicular to magnetic field means what is area vector of this coil? This is in the direction of magnetic field. Clear? So initially you can say phi 1, this is given by BA only. Clear? Because angle between B and A, that is 0. Clear? Now it is also given that we are giving here 90-degree turn to bring this plane parallel to field direction. Clear? So when we rotate it 90 degree, so at that time you can see angle between B and A, that becomes 90. So I can say flux that is passing through that coil, that becomes 0. Clear? So now here one more thing is given to you, the total charge flown in the coil and is 7.5 millicoulomb. So I can say value of Q, this is 7.5 millicoulomb. Clear? So 7.5 into 10 to the power minus 3 coulomb, this is given. Clear? And the resistance of a coil and the galvanometer, it is given, this is 0.50 ohm. Clear? Now we have to estimate the strength of magnet. Clear? So listen carefully. If I talking about induced EMF, clear? Induced EMF is actually given by minus d phi by dt. Clear? In this question it is given here, we have number of turns. Number of turns is 25. Number of turns 25. So whenever we have 25 turns, I can write like this, minus n delta phi by delta t. Clear? So we can see minus number of turns 25. What is change in flux? Final we can say 0, and initially we have BA. Clear? And divide by delta t. Delta t is given to you, yes or no? It is given here, this is millicoulomb. Okay, if nothing is given, let's suppose I am assuming total time is t. Clear? So we can say value of E, this is 25 BA divided by t. Clear? Now we can say actually this induced EMF actually having a closed loop, so we can say it is also equal to V equal to IR. Clear? I and multiplied with R. Clear? Actually we can also write like this, I, instead of I can say this is Q by T multiply R. Clear? Clear? And this is equal to 25 BA divided by T. From here I can say T and T, this one is cancelled out. Clear? And value of B is given by QR divided by 25A. Clear? Now we can place here all the values of Q, R and area, and we can get our answer. Clear? Concentrate here. Yes. So now we can say value of B we can say Q is given to you. Yes, this is 7.5 millicoulomb, clear, and multiplied with what is value of R 0.5, I can say this is 1 by 2 divided by 25 multiply A. So 25 multiply A is given, yes, that is 2 centimeter square. So 2 into 10 to the power minus 4, clear. So from here you can say, if you remove this one, I can say this is 10 to the power minus 1, clear. So this one and this one is cancelled out. From here you can say this is 3. So from here you can write like this, 3 divided by 4, and I can say this is 0.75 Tesla, clear. So this is value of magnetic field that is given by. So this is all about this question. Now dear student, we are going to discuss this question number 6.14, and my dear student, this question is very important because this question is very conceptual, as well as here we will utilize so many concepts of this chapter, clear. So now we are going to discuss this question, fully concentrate on a screen, and let us try to understand each and every concept, clear. So now concentrate. In this question it is given to you, figure shows a metal rod PQ, as you can see in figure, PQ resting on smooth rail AB, fine, and position between the poles of a permanent magnet. Permanent magnet is given to you. This is a horseshoe magnet. You can say this is north pole and this one is south pole. Okay. The rail means we can say this AB, clear. So rail number 1, second one is the rod, and third one this magnetic field, all are mutually perpendicular. Okay. A galvanometer G connects the rail through a switch K. Okay, fine, clear. Length of the rod is given to you, this is 15 centimeter, and B value is given 0.50 Tesla, fine. So resistance of closed loop containing the rod, it is also given here, and assume the field is to be uniform, clear. So first let us try to write here all the parameters that is given to you, so it will be easy for you to do some calculation, clear. Now important part here, it is given, I can actually highlight here also. Length of a rod, okay, I am writing here, length of a rod is 15 centimeter. So we can say this is 15 into 10 to the power minus 2 meter, clear. Value of B, this is 0.50 Tesla, clear. And resistance of this closed loop, resistance of this closed loop, actually this is ohm, clear, ohm. So I can say this is equal to 9.0 milli ohm, clear, and we can say this is equal to 9 into 10 to the power minus 3 ohm, fine. Now we have to assume field is to be uniform, fine, clear. Now we are going to solve part number A, clear. In part number A it is given, let's suppose this K key is open, okay, and rod is moving with the speed of 12 centimeter per second in the direction shown. So now we can say this rod is actually moving in this direction with velocity that is given to you, and velocity is here 12 centimeter per second. I can say 12 into 10 to the power minus 2 meter per second, fine. In the direction, so give the polarity and magnitude of induced EMF. First, let us try to understand. You can see, if I draw here this diagram, we can say actually magnetic field in the downward direction, velocity vector is perpendicular to this magnetic field, as well as you can see the length of this rod. Length of this rod is also perpendicular to B as well as V, clear. So I can say here B, V and L all are mutually perpendicular, clear. So it means I can write here directly this is equal to BVL, clear, yes or no? When we can apply this formula, when B, V and L all are perpendicular to each other, clear. So value of B we have, it is given 1 by 2 multiply V is given 12 into 10 to the power minus 2, and what about length? Length is given to you 15 centimeter, so 15 into 10 to the power minus 2, clear. So from here we can say this is 6, I can say this is 90, so directly you can say 9 into 10 to the power minus 3 volt, clear. So this is induced EMF that is produced in this rod PQ, clear. Now concentrate on a part number B. In part number B it is given, is there an excess charge build up at the end of a rod when the K key is open, clear. Now listen, definitely we are saying here at this time this key is open, it means there is no current that is flowing, but we know here when this rod is going in a right direction, magnetic field is acting in a downward direction, and length is also perpendicular to B and V. Clear? At the time we can see, can we find here which end is at higher potential and which end is at lower potential? Yes. Now you can see, let's suppose if I am using this right hand palm rule, at the time magnetic field is indicating in the direction of this finger. So I can see this finger representing direction of magnetic field. Clear? Like this. I can see thumb. This thumb is indicating direction of motion. At the time I can see this perpendicular inward direction, it shows the direction of higher potential. Clear? It means I can see, if I draw here, yes, if I draw here, I can see this P point, or we can say this P end is at higher potential, and I can say this Q end is at lower potential. Clear? Actually what we understand by higher and lower potential, actually we can say at higher potential means here we are having a deficiency of electrons. Clear? And here we are having that is excess of electrons. Clear? So if I say definitely we can say excess, we can say Lorentz force or magnetic force that is acting here. Clear? So when this key is open, definitely current is not flowing, but yes, definitely induced EMF will be generated. Clear? And it is also asked to you which one is at higher potential. So I can say point P is at higher potential compared to point Q. Clear to you? So now we can say what will happen if K is closed. Clear? Definitely I can say when key K is closed, at the time I can say we can assume this situation like this: a current carrying conductor is placed in a magnetic field. Clear? So when a current carrying conductor is placed in a magnetic field, I can say that conductor always experience a force. Clear? So now, so definitely it will experience a force. So B1 is complete. Now if we are going to discuss part number C, part number C given when K is open and the rod moving uniformly. Clear? There is no net force on the electrons, correct? So even when they do experience magnetic force, yes, that is true. Why? Listen carefully. Let's suppose I am saying here, let's suppose here we have a conductor. Clear? And let's suppose this conductor is moving in this direction. Clear? And I can say this is length L and magnetic field is, let's suppose, in this direction. At the time we can say, if fingers representing direction of magnetic field, clear, thumb indicating in this direction, so at the time I can say this end we are having at higher potential. Clear? And this one is lower potential. So actually a magnetic force will act on the electrons of this conductor, and initially there is no any potential difference. So as this force will act on that electron, some electron will actually move from this side to this side, and as this magnetic force will retain, I can say more number of electrons will move like this. Clear? So I can say initially we have only magnetic Lorentz force. Clear? But what will happen? What will happen with time? I can say as soon as here the more potential will be developed, definitely I can say electrostatic force also come into picture. Clear? So we can say in equilibrium condition we will find we can say QE, it should be equal to QVB. Means I can write like this: on an electron, electrostatic force that is act F equal to QE, this should be equal to minus times of EVB. Clear? I can say this one and this one cancelled out. Clear? So when this key K is open, at that time definitely I can say here magnetic force is acting, but with the time electrostatic force is also developed, and in equilibrium position we can say QVB, this should be equal to QE. Clear? So from here we can say E, this is given by VB. Clear to everyone? So this is all about this question, part number C. Clear? Now definitely in this question we have so many concepts, so concentrate properly. Now part number D, what is retarding force on a rod when key K is closed? Now listen very carefully. Let's suppose I am saying now this key is closed, and let's suppose current is flowing in this direction. Clear? Now I can say current carrying conductor is placed in a magnetic field. So I can say magnetic field is acting in downward direction. Direction of current is this one. It means I can say now force will act in this direction. Clear? This is the force acting. Clear? Now we can say actually rod is moving in a right direction and this force is acting in a left direction. That means I can say this act like a retarding force. Clear? So when this act like a retarding force, at the time I can say here retarding force this is equal to BIL. Clear? Now you can see if I write here IL cross B, clear? L vector and B vector both are perpendicular, so directly I am writing this formula. Value of B, clear? Value of B we have 1 by 2, clear? Yes or no? 0.50, clear? What about current? Clear? So current value, can we find here value of current? Yes. How can we find? Actually we know induced EMF and resistance of this closed loop, clear? Induced EMF we have already calculated here, this is 9 into 10 to the power minus 3. So 9 into 10 to the power minus 3 divided by, what about resistance? Clear? Resistance is given to you, this is equal to 9 into 10 to the power minus 3. 9 into 10 to the power minus 3. So from here we can say this is equal to 1 ampere. Clear? 1 ampere. So I is equal to 1 ampere. Now I can put this value here. Clear? And what about L? L is given in this question 15 centimeter. So multiplied with 15 into 10 to the power minus 2. So from here we can say this is equal to 7.5 into 10 to the power minus 2 Newton. Clear? So I can say this is retarding force that is acting on this rod. Clear? So this is all about part number D. Clear to everyone? Yes. Now next one. In the next question it is given how much power is required to keep the rod moving at the same speed. Clear? Now we can say definitely now you know a retarding force F is acting when we close this key. At the time if we want to move this rod with a uniform velocity, it means we have to apply some external force that is having the same magnitude as retarding force. Clear? Or I can say here we can say this F external, this is equal to F, we can say this is due to magnetic field and this is equal to BIL. Clear? And we have already calculated value of F. Clear? What is this value? This is 7.5 into 10 to the power minus 2 Newton. Clear? So 7.5 into 10 to the power minus 2 Newton. Clear? Now this is F external. Now what is my objective? My objective here is to find power. Clear? Now we have to find power when this key is closed. When this key is closed, at that time I can say we can write like this is FV. Clear? Here I am taking external. Clear? Because external force is acting in right direction and velocity vector is also in the same direction. Clear? So external force we can say 7.5 into 10 to the power minus 2 multiplied. What about velocity? Velocity is given, yes, 12 centimeter per second. So 12 into 10 to the power minus 2. Clear? So from here we can see this is equal to, we can say 60 we have 6 and we can say 90 into 10 to the power minus 4, or I can say this is equal to 9 into 10 to the power minus 3 watt. Clear? So I can say this is all about the power that is required. Clear? So when K key is closed. Clear? But what will happen when K key is open? Clear? When key is open, there is no current that is flowing in this we can say conductor, and I can say here only force that is acting, this is Lorentz force as well as the electrostatic force, and that actually acting perpendicular to the direction of velocity. So I can say here there is no external force that is needed to move this rod with a constant velocity. So when key is open, there is no any external force is required, so power dissipated it will be 0. Clear? Now if I am talking about F, now if I am talking about F, in F it is given how much power is dissipated as heat in a closed circuit. Clear? So I can say power that is given by I square R. Clear? I square R. Value of I, we know this is equal to 1 ampere, and what about R? R is given to you, yes, in this question it is given, this is 9 into 10 to the power minus 3. Clear? So 9 into 10 to the power minus 3, and this is equal to 9 into 10 to the power minus 3 watt. Clear? So I can say this much power is dissipated. Now next part is here, what is the source of this power? So we can see when circuit is closed, actually we are applying some external force, and due to that external force actually we are doing some work, and actually that work is converted here in the form of heat. Clear? Yes. Now we are going to discuss part number G. In part number G, what is the induced EMF in moving rod if the magnetic field is parallel to rails? Clear? So magnetic field is parallel to this. It means I can say now in this question it is given magnetic field in this direction. Clear? Now you can say that if we are talking about induced EMF that will be we can say that is BVL, yes or no? Or we can say yes, that is BVL. But important part is here B and V both are in the same direction. Clear? So for part number G, I am writing here, for part number G we know induced EMF, this is given by BVL, but I can say here this is we have sign 0. Clear? Because angle between B and V, that is 0. When angle is 0, I can say induced EMF will be 0 volt. Clear? So I can say in part number D, in this situation, there will be no any induced EMF that will be generated in this conductor rod. Clear? So this is all about this question. Now we are going to discuss question number 6.15, and in this question it is given to you an air core solenoid with length 30 centimeter. So length of this air core solenoid, this is given L, this is equal to 30 centimeter. Fine. Area of cross section, this is 25 centimeter square. 25 centimeter square. Clear? So this is equal to 25 into 10 to the power minus 4 meter square. Clear? And it is also given number of turns. So number of turns, this is equal to 500. Clear? It is carrying a current of 2.5 ampere. So I equal to 2.5 ampere. Clear? Now it is also given the current is suddenly switch off. Okay, it means initial current we have, this is 2.5 ampere, and finally this is 0. Fine. Clear? And in the time interval 10 to the power minus 3 second. So I can say this is 10 to the power minus 3 second. Okay. Now how much is the average back EMF induced across the ends of the open switch in the circuit? Clear? So how much is the back EMF? So actually we know, can we find here initial magnetic field that is produced in a solenoid? Yes, we know formula. This is given by mu naught and I. Clear? Here we will write I initial, but important part is here what is small n. Small n is number of turns per unit length. Clear? So we can say this is mu naught capital N I divided by L. Now we can put here values 4 pi into 10 to the power minus 7. Number of turns we have 500. Initial current is given 5 by 2. Clear? And it is divided by length we can say 30 centimeter. So 30 into 10 to the power minus 2. Clear? I can say this one and this one cancelled out. From here we can say this is 2 pi. Clear? So we can say 5 multiply 2 pi. We can say 10 pi and this one, that is 100 pi, and we can say 500 pi. So 500 pi into 10 to the power minus 5. Clear? And divided by 3. We can write like this, yes or no? So from here we can say this is equal to 5 pi into 10 to the power minus 3 divided by 3. Clear? So pi equal to what? This is near about 3.14. So we can see initial, I can say initial magnetic field, this is given by 5 into 10 to the power minus 3 Tesla. This is near about value. Clear? What about B final? B final is equal to 0 because current that is flowing, this is 0. Now definitely whenever magnetic field is changing, it means magnetic flux will change. When magnetic flux change, it means I can say induced EMF will be developed, and this is given by delta phi by delta t. Clear? So what about phi initial? Clear? Actually we can see, we can write like this area, this is delta B by delta t. Clear? Now we can put here all values and we can get our answer. Clear? So now from here we can see, we can write here E, because our objective here in this question is to find average or back induced EMF. So we can write like this. Yes. So from here we can see induced EMF equal to what? Area. Area is given 25 into 10 to the power minus 4 multiply we can say delta B by delta T. Clear? Delta B means we can say what is change in magnetic field. So directly you can say you are finding here change of 5 into 10 to the power minus 3 minus 0 and divided by delta T. Delta T means we can say 10 to the power minus 3. This one and this one cancelled out. clear, and we are getting near about value. This is 125 into 10 to the power minus 4 volt, clear, or you can also write like this is 12.5 into 10 to the power minus 3 volt, or near about 12.5 millivolt. Clear to everyone? So student, generally we will commit a mistake in this question here. Actually in this magnetic field we have already included number of turns, but here because we are talking about flux, and flux is also associated with n number of turns, clear. So here you have to also multiply it with n also, clear. So here we will multiply it with n also, clear. So now we can say number of turns we have, that is 500, so we can multiply it with 500 also, clear. So from here you can find here value 500. So at the time we can say this is 125 into, I can say that is 10 to the power minus 4 into 500, clear. So from here we can say this is 625 into 10 to the power minus 2, and I can say that is volt, clear. So this is all about this question, clear. Now student, we are going to discuss question number 6.16, and in this question it is given to you. First of all, we are going to discuss part number A. So fully concentrate on part number A. In this question it is given to you, we have to obtain here an expression for mutual inductance, clear. So objective is to find mutual inductance between a long straight wire, and a square loop of side A that is shown in a figure. Okay, fine. Now dear student, do you know how can we find here mutual inductance? Actually there is a relation between current and the magnetic flux, that phi equal to mi, clear. It means our sole objective here is to calculate first this flux, clear. So magnetic flux we will calculate, and for magnetic flux we need here magnetic field, clear. Now you know it is given in a question, we have a long straight wire. Long straight wire means I can say this is at infinity, this one is at infinity, clear to you. So from here we can say if we are talking about any element of this wire, clear, so it is having a different distance from this long wire, clear. That's why what I am doing here, I am taking a very small strip here, clear, a very small strip, and this strip is having thickness that is dr, clear. And let's suppose this is situated at a distance r from this long wire, clear. So can we find here value of B? Yes, value of B we can write like this. This is mu naught I upon 2 pi r, clear. Now what is direction of magnetic field? I can say if this thumb indicates direction of a current, then this curved finger indicates direction of magnetic field. So magnetic field direction is perpendicular inward, clear. So this is value of B. Now can we find here this area? Yes, area dA. dA is given by, we can say this is A multiply dr, A multiply dr. So now we can write like this, d phi is equal to B multiply dA. Now you can say if we are talking about area vector is perpendicular to this square loop, clear. And I can say, let's suppose area vector in the direction perpendicular inward, and B is also in the same direction. It means angle between magnetic field and area vector, that is 0, clear. So we can write like this. So from here you can say total flux, this is given by integration of B A dr, clear. Now because here variable is r, so we can say r value limit we will take from x to x plus a, clear. This is x, I can say this is a, so x to x plus a. So from here x, this is x plus a, clear. So now I can write x a plus x, value of b we have mu naught I divide by 2 pi r, clear, and multiply a dr, clear. So from here we can see value of phi, clear. So value of phi, this is equal to what? Mu naught I a, we can write like this, mu naught I a divide by, clear, mu naught I a divide by 2 pi. So I can say this is 2 pi integration, clear. Integration equal to what? This is dr upon r, clear, dr upon r, and it is from x to a plus x, clear. So I can say this is x to a plus x. So we can say value of flux, this is given by mu naught I a divided by 2 pi, clear. Now what is integration of dr upon r? This is equal to log r, so log base e r from, I can say, x to a plus x. Clear? So now we can say, we can write like this, mu naught ia divide by 2 pi log base e. Now first we will put upper limit, then lower limit. So upper limit we can say this is a plus x divided by x. Clear? Now so we can say this is value of 5. Clear? This is value of 5. So can we calculate here value of mutual inductance? Yes. Phi is given by, this is equal to mi, and this one is equal to mu naught ia divided by 2 pi log base e a plus x divided by x. Clear? I can say I and I, this is cancelled out, and from here we can write value of mutual inductance. This is given by mu naught a divided by 2 pi log base e a plus x upon x. Clear to everyone? So this is value of mutual inductance, and this is all about part number A. Clear? Now student, we are going to discuss its part number B. Clear? So concentrate on a screen. Now we are going to discuss part number B, and in part number B it is given. Now assume that the straight wire carries a current of 50 ampere. So I am writing here I is equal to 50 ampere. Fine. Then it is given to you I is 50 ampere and loop is moving to the right at a constant velocity 10 meter per second. So velocity is given 10 meter per second. Fine. And now we have to calculate induced EMF in the loop at the instant when x equal to 0.2 meter. Clear? So x equal to 0.2 meter, we have to find value of induced EMF at this value. Clear? So from here we can write like this. Actually we can utilize this formula of flux here. Clear? So I am again writing this value here, phi equal to 2 pi ia, phi equal to mu naught ia divided by 2 pi log base e 1 plus a by x. We can also write like this. Clear? Now we know induced EMF, this is given by minus of d phi by dt. Clear? So from here we can also say this is equal to minus d by dt, value of phi, this is equal to mu naught ia divided by 2 pi log base e 1 plus a by x. Clear? So now from here we can say this is equal to minus mu naught ia divided by 2 pi. Now important part is here, because this is with respect to t, can we write here in terms of x also? Yes. We can also say we can write like the dx by dt, or I can say d by dx. Clear? Yes or no? Actually I am multiplying with dx and dividing with dx. So dx by dt dot this one, and mu naught ia divided by 2 pi log base e 1 plus a by x. Clear? Now you can say this is what? This is velocity. So now I am writing E, it is given by minus mu naught ia, this is b, divided by, I can say 2 pi, mu naught ia v divided by 2 pi, and now I am differentiating with respect to x. Clear? With respect to x I can say mu naught ia divided by 2 pi and multiply 1 upon. Clear? 1 upon, this is 1 plus a by x. Clear? 1 upon 1 plus a by x, or I can say this is given by minus a upon x square. Yes or no? So from here if you simplify it, you can write like this. Actually we already write here mu naught ia divided by 2 pi. Clear? And a we already write here, this is v. So I think there is no need to write this factor again. Clear? So we will not write this again. Clear? So from here we can say we have only this term in our bracket. So from here we can write like this. This is minus minus plus mu naught ia v divided by 2 pi. I can say this is x plus a, and this is equal to, because we have here a, so this is a square. Yes or no? Yes, this is a square, and because this go x like this, so this will be like this. So now we are going to put here some values. So concentrate here. Now I will put here values and I will find directly value of induced EMF. Clear? So definitely calculations are a little bit lengthy, but we can see actually if you know concept and if your calculation is very fast, you can easily solve this type of question. Clear? So now part number A is very important for any competitive examination, but here we have to do some calculation. Clear? So if this is given by mu naught is equal to 4 pi into 10 to the power minus 7 multiply, what about current? Clear? Current value is given 50 ampere. What about A? Clear? A is given to you? Yes. X is given to you? No. Current A. A is given here. A is equal to 0.1. Clear? So this is 0.1 and 0.1 multiplied V. V is given, that is 10. Clear? Divided by, I can say this is 2 pi, value of X 0.2 plus 0.1 and 0.2. Clear? So from here if you calculate, you can say this one is 2, I can say this is 0.1 and this one is cancelled out. So from here we can say 50 into 10 to the power minus 7 into this one and this one cancelled out. Clear? So divided by, yes, divided by, I can say 0.3. Clear? So from here we can say this is equal to 500 divided by 3. Clear? 500 divided by 3 into 10 to the power minus 7. Clear? Or you can write like this, 1.67 into 10 to the power minus 5, and this is volt. Clear? So I can say this is value of induced EMF and at a position of x equal to 0.2 meter. Clear? So this is all about this question. Now student, we are going to discuss question number 6.17, and in this question it is given to you a line charge lambda per unit length is lodged uniformly onto the rim of a wheel of mass capital M and radius capital R. Fine. The wheel has light non-conducting spoke and it is free to rotate without friction about its axis. Fine. A uniform magnetic field extends over a circular region within rim. Okay, fine. It is given by this one. Okay, what is angular velocity of wheel after the field is suddenly switched off? Now forget about everything. Let's concentrate on a concept. Now we know actually we are when this field is suddenly switched off, it means there is a variation of magnetic field is there. It means flux is also changing there. So you can say definitely induced EMF will be developed, and this is given by minus d phi by dt. Clear? Okay. Let's suppose we are having a charge q, and let's suppose we have induced EMF, that is E. Clear? So can we write like this? Let's suppose if we want to move that charge along this circumference, total amount of work done, it should be equal to QE. This E is a induced EMF. Clear? And we can also write like this. If we write in terms of electric field, then we can say this is QE F, and work done equal to what? Force into displacement. We can say here total distance covered is what? That is 2 pi A. This is total amount of work done if we are moving any charge in an electric field along a circumference. Clear? So from here we can say this one and this one cancelled out, and value of electric field. Value of electric field, this is given by E divided by, I can say 2 pi A. Clear? Now we know very well E. This is given by 1 upon 2 pi A minus d phi by dt. Clear to everyone? Clear? So this is value of E. Clear? That is electric field. Clear? Now what we can do now? Clear? Now you can say phi. Phi is what? It is given by B multiply A. Yes or no? So from here you can say E. This is equal to minus 1 upon 2 pi A. This is d phi by dt. Clear? So dear student, we can say this is E equal to minus 1 upon 2 pi A d phi by dt. E is given by 1 upon 2 pi A d by dt, and I can say this is B A. Clear? Clear? That is magnetic flux. This is B multiply A. So from here we can say minus 1 upon 2 pi A d by dt B. B, and let's suppose B is a variable actually. We can write like this, area, that is pi A square. Clear? Here we have a radius A, so area is given by pi A square. So from here we can write like this, pi A square divided by 2 pi A and d by dt, and it is multiplied with b. Clear? So from here we can say this one cancelled out, this one is also cancelled out, here we have minus also. Clear? So value of electric field, this is given by minus a by 2, this is dB by dt. Clear? So this is value of E. Now actually we know one more formula. If we have electric field, at the time we can say force, this is given by QE. Clear? Yes or no? And force we can also write like this, this is m dB by dt, because our objective here is to calculate omega. Clear? So now I am writing here dB by dt Q. Now it is also given here the charge is actually situated on the rim of this wheel. So I can say Q is equal to what? I can say lambda, this is 2 pi a, and what about E? E is minus a by 2 and multiply dB by dt. Clear? So from here you can say 2 and 2, this one is cancelled out. So from here we can say mass given is m dB by dt, and this is equal to minus lambda pi a square, this is dB by dt. So dear student, now we can see we can write like this, m d by dt, and what about v? Because this charge is situated at a rim of this wheel, so we can say that is equal to r omega, and this is given by pi lambda pi a square dB by dt. Clear? So from here you can see that we can take it outside. So m r d omega by dt, this should be equal to minus lambda pi a square dB by dt. Clear? From here you can say dt and dt, this is cancelled out. So d omega, this is lambda pi a square divided by mr, and this is dB. Clear? Now if I integrate both sides, you can see if we put here some initial values, and if you find constant term you can find. Clear? But important part is here, how can we write this omega? Omega we can write here minus lambda a square divided by m r, and this is b. Clear? Now important part is here, omega equal to minus lambda pi a square divided by mr into b. This is clear to you? Now if I write here in terms of vector, I can say here this is kk. Clear? This minus sign indicates that direction of this angular velocity in the negative z direction. Clear? So this is expression of angular velocity of this ring. Clear? Again I am writing here final expression, we have omega, this is equal to minus lambda pi a square divided by mr, and this is bkk. Clear? So this is all about this question. So dear student, this is all about this chapter of class 12, chapter number 6, electromagnetic induction. So hope you enjoyed this session, and definitely if you find this solution, definitely this solution will be very useful to you to understand all NCERT concept, as well as this will be helpful to you in your competitive examination. Clear? So this is all about this session. Thank you so much.